All right, class, welcome. Today we're going to unravel the story of one of the most fundamental components in all of power electronics, the power diode. Let's get right into it. So take a look at this graph. This curve right here, this tells you basically everything you need to know about a diode's personality. Think of it as our roadmap. Our job today is to learn how to read every single twist and turn on it. Okay, so before we can even begin to decode this map, we have to ask a fundamental question. What exactly is this device we're talking about? Yeah, at its very core, the best way to think about a power diode is as a really smart one-way valve for electricity. It's the gatekeeper. It's the fundamental building block that says, yep, current, you can flow this way, but then it absolutely slams the door shut if the current tries to go in the other direction. It's just essential for everything we do. But, to really get a handle on how this gatekeeper actually works, we gotta look under the hood. We have to understand the material it's made from. And that story? Well, it all starts with semiconductors. So we start with what we call an intrinsic semiconductor. Think of it as a pure material, like silicon. It's a blank canvas, a perfect crystal lattice. But honestly, in this pure state, it's not very useful for what we need to do. The real magic, the part that makes all of this possible, happens when we intentionally add specific impurities. And there's a name for that process. We call it doping. So this doping process, it lets us create two totally distinct flavors of material. First, we've got what we call N-type material. For this, we add elements that have excess electrons. These little guys are free to move around and carry current, which is why we call it N-type for negative charge carriers. Then, on the other hand, we create P-type material. Now here, we do the opposite. We add elements that create an absence of electrons. We call these absences holes. The best way to think of a hole is like a vacant parking spot, just waiting for an electron to pull in. And as electrons jump from spot to spot, the hole itself seems to move in the opposite direction. It acts just like a positive charge carrier, hence P for positive. And what's really cool is that this isn't just some abstract theory. I mean, look at this table. We use very specific real elements from the periodic table to get this done. For example, to make N-type material, we might use phosphorus from group 5. It has extra electrons to donate. And for P-type, we'll grab something like boron from group 3, because that's what creates those electron holes. All right, so we have our two materials, N-type and P-type. The crucial point, the whole reason we're doing this, is what happens when we bring them together. The moment they touch, they form what's called a p-n junction. And this little boundary layer, this is the absolute heart of the diode. Seriously, this is where all the magic happens. Now, thankfully, we don't have to draw that block every time. In our circuit diagrams, this whole physical thing gets simplified down to this one elegant symbol. The triangle side is the anode, that's our P side. The straight line is the cathode, that's the N side. And the arrow itself, it couldn't be simpler. It literally points in the direction that conventional current is allowed to flow. Easy, right? Okay, so now that we've built that foundation, we understand P-type, N-type, and the junction, we can finally go back to that graph, back to the VI curve, and really truly understand the story it's telling us. This whole story, the diode's entire personality, it can really be broken down into three distinct operating regions. First up, we've got the forward biased region. This is when the diode is on. What's happening here? Well, we're applying a positive voltage from the anode to the cathode, and that one-way gate just swings wide open. We do need to overcome a tiny little turn-on voltage, but once we do, current just flows freely. And as you can see from the curve, it doesn't just increase, it increases exponentially. Okay, so what's next? The reverse biased region. Now the diode is off. We flipped the voltage around, applied a negative voltage, and that gate just slams shut. Now, in a perfect world, absolutely zero current would flow. But in our real, practical diode, a tiny, almost negligible amount, we call it the leakage current, might sneak through. But for almost all of our applications, you can consider that path completely blocked. But what if you push too hard? What happens if that negative voltage gets too big, if it exceeds the diode's breakdown voltage, or VBR? Well, the gate doesn't just close anymore, it shatters. The junction fails, and it fails catastrophically. A massive, uncontrolled reverse current just floods right through. And in most circuits, that means one thing: you've got a dead diode. Now, here's what's just incredible to me. This entire curve, All three of these completely different behaviors, from on to off to broken, can be described with amazing accuracy by one single elegant formula. And that is the Shockley diode equation. You could call it the mathematical soul of the diode. Let's break that equation down a bit. The IS term, that's the saturation current. Remember that tiny little trickle we mentioned that gets through when the gate is shut? That's it. And you might be thinking, who cares about a few picoamps? Well, let me tell you. In sensitive analog circuits or really low power applications, that tiny little leak can absolutely be the difference between a working design and a complete failure. It matters a lot.
And then there's VT, the thermal voltage. Its value is directly tied to temperature. At room temperature, it's about 25.7 millivolts. And this tells us something absolutely critical for any power electronics engineer. A diode's performance changes with heat. As your circuit gets hotter, this entire curve that we're looking at, it shifts. That's not a textbook problem. That is a real-world problem you are going to be managing constantly in your careers.
So this really illustrates the huge gap between the real world and our textbook models, right? On one side, you have the practical diode. It's governed by this equation, it needs a little voltage to turn on, it's got that tiny leakage current, and it has a very real breakdown limit. On the other side, you've got the ideal diode. It's a perfect switch, turns on with 0 volts, has 0 leakage, and it can block infinite voltage. It's a fantastic tool for a first-pass analysis, don't get me wrong, but we have to remember, it's a fantasy. Okay, so let's recap. What's the big takeaway here? A diode isn't just a component you pull out of a drawer. It is a precisely engineered PN junction that acts as a one-way street for current. And its entire story, its on-state, its off-state, and even its self-destruct mode, is captured perfectly in that VI curve, which is all modeled by that single, elegant Shockley equation. So, I want to leave you with a final thought to chew on. If the ideal diode is a perfect switch, why do we spend so much time obsessing over the imperfections of a practical diode? I'll tell you why. Because as engineers, we don't design for the ideal. We live and work in the real world. And it's these practical limits, the forward voltage drop, that reverse leakage current, the breakdown voltage, all the effects of temperature. These are the things you will spend your entire careers managing. Understanding the real diode isn't just an academic exercise. It is the very essence of what it means to be a power electronics engineer.